All right, so we're going to wrap up the current section on advanced bivariate applications. And so we're going to be actually looking at the inference for regression today. So let's get going with it. Excuse me. So let's just talk about B. B is a population, of course in this case it's capital, it's like beta. This is the rate of change in the mean response as the explanatory variable increases. It is a parameter, it's the population value. And we're going to use inference techniques, specifically t-tests for linear regression and t-intervals for regression, in order to do tests of significance, or, in order of what I said, do estimation. So that's what we're going to be doing. We don't know what this true slope is for the population relationship or the rate of change, but we can work off of sampling, and that's what we're going to do. So confidence intervals for the slope and regression will give you a range of values where we believe the true slope or beta might fall, and we're going to be such and such confident, so that if we are 95% confident, that means if we were to repeat building confidence intervals with different samples of the same size, that out of, say, 100 of them, we would expect 95 to actually capture the true slope for the population. You know how this works. So here is our formula for it. And although we're going to be pretty reliant on the calculator, knowing the formula here is pretty important. Now it looks kind of strange and unusual, but it's really going to be in the same general format as all confidence intervals. Here's our sample estimate. That's what we get when we run a linear regression and get the slope of the LSRL line from our ordered pairs. Plus or minus, this will be the margin of error. The margin of error is going to be the standard error of B times a t-star value that is going to be based on the confidence level. And just don't forget, we have n minus 2 degrees of freedom. So B estimates the population parameter beta. T star is the upper 1 minus c divided by 2 critical value with n minus 2 degrees of freedom. All right, so this is much like the t star would be for a confidence interval for means, except there we would only have n minus 1 degrees of freedom. All right, so you can get the chart and figure out the t-star number, or you can do 1 minus the confidence level, right? So if it's 98%, it's 1 minus 0.98 divided by 2, and that would be inverse t for that, only it would be the opposite, so that we would be this would, goes left to right, so we want to have the right tail of this, and then 2 degrees of freedom. All right, this is the formula for standard error of B. We're going to get this on computer output, or we can use formulas to get it. Our calculator will give it if it's an NSpire. If it's a TI-84, then we can use a formula, all right? But it involves getting S, so you kind of have to get that first. And again, this is a neat formula, but we don't ever really use it. So here is your standard error of B, right? Standard deviation, slope, standard error of B. This t value, it comes from the B value divided by the standard error of B. Right, and you'll see that when we get to tests of significance, and then it would just be a TCDF, from here to infinity, with 2 degrees of freedom, and this would give you a p-value, which again we'll get to. So this is our example. We're going to be using the speed in feet per second of a runner to predict their steps per second. And we're going to do this with a 99% confidence to estimate where the true slope might be. So I'm going to get out of here, and I'm just going to kind of run this for you so you can see it. I've got this already set up in the calculator, speed, steps, and everything is in correctly. And we're just going to go ahead and run the confidence interval. So it's menu, and whoops, check that. Let's go to the home screen and open up a calculator page. Now we can go to menu, statistics, and confidence intervals, and we want a linear regression T-interval. All right, we're working on the slope, right? So remember, b plus or minus t star times the standard error of b, so it is slope. All right, so we're using the speed of the runner to predict their steps per second. This will store the equation if we want to use the LSRL to make predictions. And remember, this was 99%, so 0.99, and tab to OK. All right, let's see what we have. All right, so here is the lower value in the confidence interval. Here's the upper slope, margin of error. So the middle of this interval will be the 0.080284 plus or minus 0.006519. And you'll notice that 0 is not in here. We'll get to that in a minute. 5 degrees of freedom, right? So we must have 7 ordered pairs. Here's that S value, which is the standard deviation of the y's. Here's the standard error of the slope. Here's A, R squared, R, residuals. So we can, check all of the assumptions, but let's hold off on that for the moment. And so let's go ahead and see where this ends up. So from current. All right. So we have to define beta, right? That is the true average rate of change of steps per second for every 1 foot per second increase in speed. Sometimes these things are a little hard to define. And here is the neat part. You already know the 4 assumptions. We learned them yesterday. We don't need to list them. All we need to do is just say assumptions for inference are considered to be met, or assumptions assumed to be met for inference. We do need to name it, so linear regression T-interval, and we just write out what we got, all right? So it goes from 0.0738 to 0.0868 with 5 degrees of freedom from a lin-reg T-interval, you saw that. And then we need the usual spiel, right? So we're 99% confident that the true average rate of change of steps per second for every foot per second increase in running speed lies in the interval from the 2 numbers that we got. That's a mouthful, but it's context, 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 all right? If we've spared you from having to do the assumptions and you can crank this out in your calculator, the least I can get from you is a correct interpretation. All right, if you leave that off, what to do? All right, but remember, this is a slope, so true average rate of change of something, okay, per something. Now, the other thing that we have to do is we have to look for 0, because at 0, there's no linear relationship. If 0 were in here, we would have evidence that there's no linear relationship between these 2 things. We don't find 0 there. In fact, they're both positive. So we have to add on this extra statement. Since 0 is not contained in the interval, there is evidence of a positive predictable linear relationship. All right? Positive because both of these are positive. Simple. Okay? So we have to check for 0 here. Otherwise, what would be the point? Okay, so why 0? A slope of 0, if it shows up, if it's something that's really in your scatter plot or in your LSRL, that just tells you y doesn't tend to change linearly when x changes. In other words, when x changes, y is just behaving randomly. That means you have no linear association between the 2 variables, all right? And in your LSRL, if the slope were 0, remember y equals a plus b times x. Well, if that b is 0, it's just going to be, I meant to say y hat. Y hat equals a. And that's not much of a regression equation. So looking for 0 is the thing to do in a confidence interval. So if 0 is captured within the interval, then you will need to write, since 0 is contained in the interval, there may not be evidence of a predictable linear relationship. Okay? Follow those scripts. You can't go wrong. All right. That was so easy, we can do hypothesis tests of no linear relationship at the same time. Remember our chi-square test of independence was that HO is that the variables are independent, meaning that they're not related, no relationship. All right, this is the same thing. We're looking for a test of no linear relationship. So that will be HO, right? That beta equals 0, which means no linear relationship. So define B, or beta, right? We always do that. Hypotheses, beta equals 0 for HO, meaning no linear relationship, which fits all the other things. No effect, no change, no difference, no relationship, no linear relationship. All right, the alternative is always directional based on the wording of the problem, okay? So if they ask you, is there evidence of an increasing slope or a positive relationship, then that will be your HA. If HA, or if they mention decreasing slope, then that means you'll have a beta less than 0 for HA. Now they may actually say, do you have evidence of a linear relationship, which means it could be increasing or it could be decreasing, in which case it's a not equal to. All right, you don't have to list and check assumptions anymore, not for this. For all the other things you do. And that's mainly because if it shows up on an AP exam, it does take time to check them. Not a lot, but it does take some time. So unless asked to check assumptions, you may say conditions necessary for inference are considered or assumed to be met. All right, again, they may ask you to do it. All right. So that will be, let's see, it was, what was that first one? I'm just drawing a blank. I remember the second one. It's that all the y's are normally distributed for each x in your scatter plot, and that there's a constant spread in your scatter plot from beginning to end, and that you have independence. And what was that first one? This is totally left my mind. But in any event, if it comes to me, I'll come back to it. All right, so here's how to check. Oh, linear. Duh, that's the most obvious one. Scatter plot looks reasonably linear. Equal variance. Residual plot has a constant spread. Normality. Remember, normal probability plot of the residuals. And then independence, if you have a simple random sample, that's going to verify your independence. I can't believe I didn't know linear. That's lame. That's lame. All right, so we're going to use a t-distribution with n-2 degrees of freedom, okay? Okay, so here is your t-test statistics. This is what we normally would see. Observed minus expected divided by standard error, and that will give you a t-value. Now, since HO is that beta equals 0, this just disappears, and we get t equals b divided by the standard error of b. This is what we typically use. It's not too often where you'll get a question is, do you have evidence that the slope is greater than 3? Or equal to 4 or -2. It's always, is it 0 or not? So this is what we'll use, but this will give you some basis to understand how this relates back to other test statistics and why this beta vanishes. All right, if beta is any other value other than 0, use the first equation and you will have to solve by hand to get the test statistic. You know what, typically, I never see where the HO is anything other than 0. So I don't think I'd worry too much about that. And then if we get a t-value, you can just use a t-CDF to find the p-value. All right. Just remember, if it's going to be a not equal to, you have to double the p-value. Okay. If not, then it's just going to be from your t value to infinity or from negative infinity to your t value. And the conclusion is just like it always is. All right, this is going to be the same set of data. It says conduct a two-tailed hypothesis test. So that's a not equal to. Alpha's 0.01 to determine if the speed in feet per second of top female runners predicts the number of steps per second they take, per second. So in other words, is there a linear relationship, a predictable linear relationship? So let's see what we've got here. All right, define B, or beta. That's what we did in the previous problem, so it should be the same. All right, HO is that beta equals 0. That means that the two do not have a linear relationship. And HA is that it doesn't equal 0, so it may be positive, it may be negative, it's just not 0, okay? All right, assumptions necessary for inference are considered to be met. Yes, always like that. Name it, because we're all calculator based here. All right, so we're going to get a t value, we're going to get a p value, and I will show you this on the calculator with degrees of freedom. And this is way less than 0.01, so we're going to reject. We're going to reject HO, which means that we will have evidence of a linear predictable relationship between the two variables. So since P is less than alpha, the result is significant, and we reject HO, we have sufficient evidence to believe that for top female runners, all the context here, there is a predictable linear relationship between the number of steps for every 1 foot per second increase in speed on average. Okay? Yeah, since we're dealing with slopes, then we can throw in the on average. All right, let's go and take a moment's pause from this, and we'll come back, and I just want you to see what we do on the calculator. All right, so I've got the original data still sitting in here, so I can go ahead and run that linear regression t-test. So I'm going to go here. This is the confidence interval I did previously, and just go ahead and run the test. So menu, statistics, stat tests, and linear regression t-test. And let's see, I'm using speed to predict steps per second. And I don't know why that's so far out there, so I'm just going to store that in F2. And then since it's a not equal to, I'm going to leave that where it is. If I needed to change it, here's greater than, not equal to, and less than, but I want the not equal to. So I'm going to hit OK. It'll take that, OK. OK, so what do we have? Here's that t value that you saw in the PowerPoint. Here's that tiny little p value. 5 degrees of freedom, yay for that. You have A, B, S, standard error of the slope, and all the things that you know you want. So that's how you use the calculator for it. And we'll just come back to the PowerPoint. And I think we're right there. So, all right. So calculating standard error of B. It comes up in the n-spire, but it does not come up on the TI-84. So what we can do is rearrange this formula. We can multiply each side by the standard error of B and then divide each side by t. So you get a different version of that formula. So you will get B and you will get T, and if you make a ratio out of it, you can get the standard error of B. Really simple. Okay, but you got to remember it. So this one was 0.0803. That was the slope divided by 49.6582, and there's your standard error of B. So what the calculator does. So interpreting it, this is the standard error of the estimated slope parameter. In other words, what's happening here is if I get a sample and get a bunch of ordered pairs from my sample and generate everything that I need, I'll get, just run an LSRL, I'll get a slope, right? A lowercase b value. If I do it again with a different group of people, then I'll get a different slope, slightly different. And if I do it again, I get another one. And if I do it again, it's highly unlikely I'd get the same slope from sample to sample to sample. That's the error that we see in sampling. And that's what this is quantifying. That's the standard error of the slopes that we get from repeated sampling. So it estimates that error. So the standard deviation of the estimated slope for predicting speeds in step per second by using feet per second is what we just calculated. All right, so this value estimates the variability in the sampling distribution of the estimated slope. How much we would expect sample slopes to vary from experiment to experiment, which is kind of how I led the slide. Now, don't mix this up with interpreting S. S is a feature of your scatter plot, all right? It just gives you an estimate for the spread or it's really a standard deviation that your y values have around the LSRL at your x values, at any given x. And we just assume that that's going to be consistently the same all throughout the population, scatter plot. So this is the standard deviation of the residuals. And this statistic measures the variation of the steps per second for the given speed in feet per second of top female runners. So it's just the variation in that output. Okay, so that concludes what we learned for the year. That's it. That's everything. So tonight's, for tonight and over the weekend, it's worksheet number 2. Then on Tuesday, it's going to be asynchronous. I won't have anything new to teach you, so please don't sign in to Zoom. All you're going to do, you don't have to watch a video unless you want to go back and review something. All you got to do is keep doing the homeworks. I will then see you on Wednesday, and we'll do a wrap on this. And Thursday is asynchronous also. So just do whatever the calendar tells you to do. We won't be meeting. There won't be a video unless I decide to do some kind of a extra review thing. And then we're going to have our test on Friday. Okay? So let's call this a wrap. And I appreciate you watching.